积极探索和开拓创新，讨论碰撞和相互激发，人才发展和融合生态。查斯乌科技网站汇聚全球高价值科技和学术信息，提供多种模式智能高效服务，链接全球学术、技术和人才资源，链接、创新、激发、融合。查斯乌科技网站与你携手并肩，共同促进全球科学和技术的进步。科学和技术的进步源自于什么？是在实践中的启示，是在探索中的火花，是在碰撞中的激发，是在融合中的升华。1654年，帕斯卡和费马在分补助问题的讨论中，开启概率论的大门。1687年，牛顿在哈雷的鼓励下，积极研究并最终出版《自然哲学的数学原理》。1736年，欧拉走过哥尼斯堡七桥，并开创图论这门新的学科。20世纪初期，爱因斯坦和波尔在相爱相杀中，分别开拓广义相对论和量子力学。1936年，图灵在研究可计算数的过程中，开始图灵通用机的探索。1945年，参与了曼哈顿计划的冯诺依曼带来计算机领域的三定律。1948年，香农在和冯诺依曼的讨论后提出信息熵和香农定理。20世纪初期，菲尔兹在证明黎曼罗赫定理的同时，致力于全球数学交流。1941年，海蒂拉玛和安泰尔发明的调频技术落地于无线通信系统。1965年，戈登摩尔总结实践经验，提出了一直被追赶的摩尔定律。2000年，高空推动建成世界上第一条1公里长的光纤网络。1986年，杰弗里·辛顿将反向传播技术应用于深度学习。科学研究和技术发展就是这样一步步向前迈进。链接实践和整合资源，积极探索和开拓创新，讨论碰撞和相互激发，人才发展和融合生态。查斯乌科技网站汇聚全球高价值科技和学术信息，提供多种模式智能高效服务，链接全球学术、技术和人才资源，链接、创新、激发、融合。查斯乌科技网站与你携手并肩，共同促进全球科学和技术的进步。科学和技术的进步源自于什么？是在实践中的启示，是在探索中的火花，是在碰撞中的激发，是在融合中的升华。1654年，帕斯卡和费马在分补助问题的讨论中，开启概率论的大门。1687年，牛顿在哈雷的鼓励下，积极研究并最终出版《自然哲学的数学原理》。1736年，欧拉走过哥尼斯堡七桥，并开创图论这门新的学科。 20世纪初期，爱因斯坦和波尔在相爱相杀中，分别开拓广义相对论和量子力学。1936年，图灵在研究可计算数的过程中，开始图灵通用机的探索。1945年，参与了曼哈顿计划的冯诺依曼带来计算机领域的三定律。1948年，香农在和冯诺依曼的讨论后提出信息熵和相容定理。20世纪初期，菲尔兹在证明黎曼罗赫定理的同时，致力于全球数学交流。1941年，海蒂拉玛和安泰尔发明的调频技术落地于无线通信系统。1965年，戈登摩尔总结实践经验，提出了一直被追赶的摩尔定律。2000年，高锟推动建成世界上第一条1公里长的光纤网络。1986年，杰弗里·辛顿将反向传播技术应用于深度学习。科学研究和技术发展就是这样一步步向前迈进。链接实践和整合资源，积极探索和开拓创新，讨论碰撞和相互激发，人才发展和融合生态。查斯乌科技网站汇聚全球高价值科技和学术信息，提供多种模式智能高效服务，链接全球学术、技术和人才资源，链接、创新、激发、融合。查斯乌科技网站与你携手并肩，共同促进全球科学和技术的进步。科学和技术的进步源自于什么？是在实践中的启示，是在探索中的火花，是在碰撞中的激发，是在融合中的升华。1654年，帕斯卡和费马在分补助问题的讨论中，开启概率论的大门。1687年，牛顿在哈雷的鼓励下，积极研究并最终出版《自然哲学的数学原理》。1736年，欧拉走过哥尼斯堡七桥，并开创图论这门新的学科。20世纪初期，爱因斯坦和波尔在相爱相杀中，分别开拓广义相对论和量子力学。1936年，图灵在研究可计算数的过程中，开始图灵通用机的探索。1945年，参与了曼哈顿计划的冯诺依曼带来计算机领域的三定律。1948年，香农在和冯诺依曼的讨论后提出信息熵和相容定理。20世纪初期，菲尔兹在证明黎曼罗赫定理的同时，致力于全球数学交流。1941年，海蒂拉玛和安泰尔发明的调频技术落地于无线通信系统。1965年，戈登摩尔总结实践经验，提出了一直被追赶的摩尔定律。2000年，高锟推动建成世界上第一条1公里长的光纤网络。1986年，杰弗里·辛顿将反向传播技术应用于深度学习。科学研究和技术发展就是这样一步步向前迈进。链接实践和整合资源，积极探索和开拓创新，讨论碰撞和相互激发，人才发展和融合生态。查斯乌科技网站汇聚全球高价值科技和学术信息，提供多种模式 智能高效服务，链接全球学术、技术和人才资源，链接、创新、激发、融合。查苏科技网站与你携手并肩，共同促进全球科学和技术的进步。科学和技术的进步源自于什么？是在实践中的启示，是在探索中的火花，是在碰撞中的激发，是在融合中的升华。1654年，帕斯卡和费马在分补助问题的讨论中，开启概率论的大门。1687年，牛顿在哈雷的鼓励下，积极研究并最终出版《自然哲学的数学原理》。1736年，欧拉走过哥尼斯堡七桥，并开创图论这门新的学科。20世纪初期，爱因斯坦和波尔在相爱相杀中，分别开拓广义相对论和量子力学。1936年，图灵在研究可计算数的过程中，开始图灵通用机的探索。1945年，参与了曼哈顿计划的冯诺依曼带来计算机领域的三定律。1948年，香农在和冯诺依曼的讨论后提出信息熵和香农定理。20世纪初期，菲尔兹在证明黎曼罗赫定理的同时，致力于全球数学交流。1941年，海蒂拉玛和安泰尔发明的调频技术落地于无线通信系统。1965年，戈登摩尔总结实践经验，提出了一直被追赶的摩尔定律。
Okay, so it's already 6:30, and I think we could now begin. And so, hello everyone, and welcome to the lecture 10 of the Evolution of Physical Layer Communication Waveforms course series. So today, we are very honored to have Professor Yifeng Xiong as our guest speaker to give a talk on our new ISAC waveform called the autocorrelation function K. So before we start, let me first briefly introduce Professor Xiong. So Professor Xiong received his PhD degree in University of Southampton, UK in 2022, and received his bachelor and master degrees from the Beijing Institute of Technology in 2015 and 2018, respectively. So he is currently an associate professor at Beijing University of Posts and Telecommunications. So Professor Xiong is famous for his work on information theoretical limits, on integrated sensing and communication. So his work has won the prestigious award of 2025 HVE Communication Society and the Information Theory Society Joint Paper Award. And also he has won the Best Master Thesis Award of Chinese Institute of Electronics and the Best Paper Award of HVE CSC ICCC 2023. Okay, so without further delay, let's welcome Professor Xiong again to give us a talk. Okay, so Yifeng, the stage is yours.
Thank you, Fan, for your very exciting and warm introduction. And okay, so today, what I would like to share with you is that our recent work on the basically trying to control the peak side lobe of the ISAC waveform, but the waveform itself is actually the so-called payload bearing, in the sense that it actually carries information that are actually modulated by random symbols, like just like the conventional communication symbols. Okay, So in this sense, we are actually, from the perspective of communication, we are actually designing the so-called modulation scheme. So in this sense, that's why we call this scheme autocorrelation function key. So before we start, before we dive into details, let us just briefly introduce the background of ISAC. So ISAC is actually one of the 6 key usage scenarios of the 6G. It's actually becoming a fundamental capability of global networks and supporting a large amount of international standardization, and it's improving the spectrum efficiency of the network. And actually, it supports a large number of emerging applications, such as intelligent transportation, industrial automation, and digital twins. So in short, what is ISAC? ISAC is basically simultaneously communicating information and senses the surrounding environment. So in this sense, it can actually improve the spectral and hardware and energy efficiency because it's actually implementing the 2 functionalities on a shared platform. So recently, the focus of the ISAC community is shifting to the so-called COM-centric or communication-centric ISAC. This is a paradigm actually trying to implement ISAC by modifying very slightly the existing communication systems. This is very reasonable because if we're trying to build 6G networks, we would actually we will expect to modify very slightly the original network in order to just keep the cost minimal. Okay, so actually in 5G Advanced, the ISAC functionality has been already added to the network, but only in its very preliminary form, in the sense that currently we are actually exploiting the physical layer reference signals, such as the CSIRS, DMRS, PDRS, and etc. in this sense, or actually some of the companies are actually they're promoting for the technique that using the dedicated reference systems for sensing, but all these reference signals are only they're only occupying a very small portion of the time frequency domain resources, because after all, this is a communication system, so we have to actually allocate most of the resource, most of the time frequency domain resource to the data payloads symbols. So that's why all these reference signals only occupy like 10% to 15% of the resources. So in this sense, we really wish to actually use all these remaining degree of freedom, these data payloads, to actually enhance the possible achievable sensing performance. But this actually will bring us a new challenge, because these reference signals themselves are actually deterministic. So these deterministic signals can be well designed in the sense that we can actually shape it to any degree. But if we have to use data payloads for sensing, since all these signals has to be random, in the sense that they can carry information, we have to compromise the sensing performance to a degree, because we cannot actually design the payload bearing signals in a fully manner. We have to design it to a certain degree. So that's the main challenge. So to start with, let us consider this very simple model, this simple but quite general model, which corresponds to the classical problem of target ranging. So basically, it's estimating the distance of a target. Okay, so for the signal modeling, we consider a slightly restrictive, but actually still quite general class of signals, in the sense that we have a so-called cyclic prefix before the signal block. So this kind of signals are not actually restricted to the conventional OFDM. We also basically we all know that OFDM has a CP, the cyclic prefix, but actually, for example, OTFS and AFDM and all and maybe simply single carrier modulation with CP, which we call it CPSC. All these signal models, all these signals, they all have CP. So in this sense, we can consider this frequency domain channel model in the sense that here this is the communication channel. This is a frequency domain channel. It is directly entropy-wise product multiplied to this frequency domain representation of the signal. Okay, so that's because the interference between the intersymbol interference can be cancelled by using the CP technique. After CP removal, we have this no ISI representation of the channel. Okay, so this is basically the communication channel, and NC is the additive wide Gaussian noise. And on the right hand side, this is the sensing channel. So HS is the sensing channel, but we do not assume that HS is known, because the sensing channel is something that we have to estimate, right? Okay, but here we don't consider actually the channel estimation error as the performance metric, because the channel actually in sensing, in terms of sensing, we're not really care about the entire the global MSE or the global estimation error of this channel, as we will see later. So what we do consider is that we consider the so-called normalized periodic autocorrelation function as listed here. So this guy, what is this guy? So basically, in ranging or in target estimation, distance estimation problem, what we do is that we first perform the so-called match filter. This is a very classical module in this ranging signal processing pipeline. So after doing the match filtering, what we have at hand is actually a series of target responses, and all these responses are actually a weighted sum of this so-called normalized periodical autocorrelation function, and all this weighted sum, they are actually shifted in time, because all these targets are actually, they have different distance from our base station, and this distance will translate into delay. Okay, so what we do really need to characterize is that this autocorrelation function is not the so-called ideal the ideal Dirac delta-like function, because in that sense, this Dirac delta-like function will not have inter-target interference. So this is what we do really need to consider. Okay, so what does these side lobes, which is actually the inter-target interference, so how does this interference have an influence on our target detection performance? So it turns out that we have to consider the so-called CFAR-like estimators. So CFAR stands for constant false alarm rate. These kind of estimators are actually the most popular target detectors. So in short, these kind of detectors are actually using sliding windows. They slide through the received signal, and after that, you're going to have some response. And on the if you look at the bottom, the figure at the bottom of this slide, you will see that, okay, at some point there is going to be a peak. Okay, there's going to be a peak. So if there is a peak that is high enough to surpass some threshold, the threshold is here, and the threshold is actually something calculated from the statistics in the sliding window. Okay, so as long as there's something that surpasses this threshold, so we recognize this thing as a target. Okay, so if you think of it, you will see that if there is a lot of inter-target interference, then if there is a strong target that is strong enough such that there is a weak target, that the weak target's response is even lower than the side lobe of the strong target, then you will see that, okay, the adaptive threshold in the vicinity of this weak target is so high such that this target is invisible to the detector. So basically, in that case, if you have high side lobes, then there is going to be a rise of your local detection thresholds. So in that sense, you will have these weak targets less detectable. So that's harmful. So that will take us to the design of so-called the low ambiguity or low side lobe waveforms, right? So actually, these low ambiguity waveforms has been already a very hot topic in the area of radar signal processing and also in the area of sequence design. But in these areas, all these sequences or waveforms, they are deterministic. But in our problem, we're considering payload bearing signals. So in this sense, we have to consider some random signals. So that's why we have to consider some slightly different performance metrics from the classical ones, right? So one natural choice is that we could consider a so-called expected side lobe level, in the sense that it is actually the mean squared value of these side lobes, right? This is a mean squared value is expected. So that's one choice. You could also say that it's the average side lobe level. Okay. So there's yet another choice that's called the peak side lobe level. It's also owing to the radar literature. But in our case, if you look at it, you will see that, okay, PSL, the peak side lobe level, is simply the maximal value of all the side lobes. However, this thing in our case is actually a random variable, because all these side lobes themselves are actually random. So their maximum is also random. So that's why we have to investigate its CDF, right? We can also consider something different by simply maximizing all possible realizations of our input signal X. And in this case, we have this maximal PSL, right? It's a double maximization over both X and K, the indices of the side lobes, right? So historically, people have actually first focused on the problem of minimizing the expected side lobe level, the ESL. But actually, in particular, people started from the so-called expected integrated side lobe level, because this guy is actually a scalar. Because ESL is something that depends on your index of your side lobe bin, right? So EISL is simply the sum of all ESLs. You could view this guy as an average ESL. Okay, so in this case, what we could do is that we could actually design a so-called orthogonal modulation schemes. So these orthogonal modulation schemes, if you are familiar with communication, then you will know that this will encompass like CPSC, the CPOFDM, and AFDM, and things like that, right? This guy encompasses a large class of different waveforms, all right? So in this case, if you're going to minimize the average ESL or the EISL, it amounts to actually design a so-called waveform basis matrix, which is actually a unitary matrix U. So in this case, we have X is actually the multiplication of this basis U and a vector that contains our actually IID data symbols, which are drawn from IID from a so-called constellation set C, right? This guy, basically, it corresponds to the constellations that we are familiar, like PSK or QUAM, things like that. Okay, so after that, what we do is that we try and solve this minimization problem. So basically, we minimize the EISL, and the EISL can be actually rewritten in this form, which is actually a function of our waveform basis U here, and we simply minimize over all possible unitary matrices which construct this so-called nth order unitary group, and we're trying to find the optimal U in this case, right? So the objective function is actually basically the EISL, and it corresponds to the sum of all possible shifted version of the response, right? So here JK is the k's time shift operator, which shifts k delay units. Okay. So it turns out that actually in one of our previous works, we have shown that OFDM turns out to be the only waveform that achieves the lowest EISL for all sub-Gaussian constellations. So basically, all our familiar constellations like PSK and QUAM, they're all sub-Gaussian constellations. So this is quite general. So basically, OFDM is the EISL optimal waveform. And furthermore, we have also managed to show that OFDM is also the only waveform that actually achieves the lowest average side the average side lobe level at every delay index, right? So it is also ESL optimal everywhere. So this is quite strong. But the point is that we're considering ESL. We are not considering other performance metrics, okay? But here is the question. So what is actually the direct operational meaning of ESL? It turns out that in the first place, we have some intuitions about ESL because it's like the variance of the side lobes. It corresponds to the variation of these different side lobes. But all these intuitions, they do not themselves translate into the so-called detection performance itself, right? So we have to consider the direct detection or estimation operational meaning. So it turns out that in one of our recent works, we managed to prove that actually OFDM is also optimal in the sense of CRB, which is the Kramer-Rao bound. It is actually the lower bound of estimation MSE. So it is actually an estimation theoretic performance metric. And it turns out that actually the CRB gap between OFDM and an arbitrary waveform U, which is actually a unitary matrix, is somehow related and closely related to the EISL gap between OFDM and that U. So in this sense, you could, roughly speaking, you could say that the EISL can be viewed as some unweighted CRB, okay? So it's somehow related to the estimation performance. So that brings us the operational meaning of ESL. However, there is some actually limitation of CRB, right? So CRB has some limitations. So that also translates to ESL. So basically, first one, that the CRB is only tight in the high SNR regime. So that's one of the problems. Besides, CRB is also only an estimation theoretic bound. So it actually does not directly apply to target detection. So if we are considering target detection, and in particular in the low SNR regime, then we cannot actually consider ESL, right? So that actually motivates us to consider the PSL. So here is the intuition. So basically, on the left-hand side, you will see that if we are going to control the ESL to a degree, we will see that the average side lobe level in blue is quite low. However, there can be some local high side lobes. So in that case, if we're going to use a low enough threshold, then this high side lobes will be recognized as a target, but that will give us a false alarm. So that's harmful. However, on the other hand, if we're going to use a high enough threshold, then some weak targets will be disappeared, right? So that's the point. However, on the right-hand side, if you are going to control the PSL, you will see that although the average side lobe level is higher, you will see that if you all these side lobes are actually bounded, right? There is no local high side lobes, so there is no spurious target detections. We do not have these false alarms. So that will, at least intuitively, give us some evidence that's why PSL can be more reasonable in target detection. Okay, so in light of this, we propose this problem. So for ISAC, what we wish to do is that we wish to maximize the achievable rate for communication. However, at the same time, we control the PSL, right? This is the problem. So what we do is that we simply maximize the mutual information between the input signal and the output, the output of the channel, of the communication channel, right? This is basically the achievable rate. And the constraints is twofold. In the first one, in equation 1b, this guy here, F1, corresponds to the main lobe of the ACF, of the autocorrelation function, which by application of the Wiener-Keynesian theorem, it is actually the energy of the entire code word or the entire waveform. So you could view this guy as the energy constraint. So this is actually very you could see this everywhere in communication theory, right? So here 1C, the constraint 1C is actually the heart of this problem. It is basically a PSL constraint. You will see that, okay, apart from the main lobe, all the side lobes, their magnitude squared is less than 1 over n times zeta ACF for all side lobes. So basically, zeta ACF is something that we could actually design for. It is a so-called attenuation factor. We could, if we would like to reduce the PSL to a higher degree, then we simply increase this attenuation factor. Okay, so basically the problem is a PSL constraint mutual information maximization problem, and its form is clean and simple. The only bad news is that solving this problem is almost impossible. It's very difficult. However, fortunately, if we consider the case that the communication channel is high SNR, so if the communication channel is in the high SNR condition, then it is possible that we approximate this mutual information maximizing input distribution by the so-called the maximal entropy input distribution. So in that case, our problem is going to be like maximizing the so-called differential entropy of the input distribution, and this guy is much more simpler than this mutual information maximization problem. Okay, so that's why we have actually managed to prove this thing. It turns out that in the high SNR regime, if we would like to have a capacity achieving strategy, then it turns out to be the maximal entropy input distribution, and this distribution is characterized as follows. So if you have a high SNR regime that the power of this noise tends to 0, then you will see that, okay, this capacity input achieving input distribution can be factorized into two parts. The first part here, the P prime of P prime, this guy corresponds to the power spectrum. And the right-hand side, the p theta of theta corresponds to the phase of the spectrum. So basically, the phase of the spectrum and its magnitude can be separated, right? That's a good news. So if you look downwards, you will see that, okay, the distribution of the phase is quite simple. This is basically a uniform distribution over the so-called n-dimensional torus. Basically, that's an interval between 0 and 2 pi, right? So basically, all these phases are entirely uniform. So that's quite simple. However, if you look at 2b, this guy is more involved, right? We don't really read anything meaningful from this. So that will bring us a question that how do we actually implement this distribution? That's the problem for our practical implementation, right? So after that, what we have considered is that we consider this very special case. We could consider this case that the communication channel is so-called frequency flat. So this channel, in this channel, we have this the magnitude of this channel proportional to 1, which is constant. So in this case, actually the asymptotically optimal input distribution becomes the uniform distribution over the entire visible set. So in that case, if you look backwards here, right? Here, in this case, we have all these HCI corresponding to the constants. They are constants. Then this guy becomes a uniform distribution. Okay. So that's why we have to study this feasible set. So it turns out that this feasible set can be further decomposed into some constraints, into more constraints, right? If you look at it, then we have this guy, this pi is larger than or equal to 0, which corresponds to the so-called non-negativity of your power spectrum, which is reasonable. And the second one is that you're going to have all these side lobes, right? All these side lobes less or equal to some constant t. Okay, so that will be a problem because if you're going to actually generate this uniform distribution, although it is conceptually very simple, you cannot really implement this in a computationally efficient manner because, for example, if you consider the so-called random coding strategy, which is very popular in information theory, then this guy is, you can actually do this. You can actually construct this so-called random codebook technique, but that is only conceptually clean. It is not algorithmically attractive because if you're considering the decoding of your random coding, then the decoding complexity will be exponential. So it is prohibitive for our actually the real-time coding. So that's why we cannot really use this direct codebook. You cannot use this direct random codebook strategy. So the key idea here is that actually the phase is quite simple because you can simply use something like PSK to simply sample from the uniform distribution of it. But if you're going to sample from the uniform distribution over this spectrum power feasible set, then that will be a problem because these two constraints, basically the side lobe constraints and the power non-negativity constraints, they are coupled to each other. Okay, so that's why what we could do is that we could transform our viewpoint. So we could actually make use of a change of coordinates towards this ACF domain. So basically, we use the inverse DFT relation, and what we have is that okay, now we transform our viewpoint to the ACF domain, and we see that all these side lobe constraints are actually separable, right? So these guys can be basically you could view those as IID symbols. Okay, so in this case, the only constraints that is remained globally coupled is the power spectral non-negativity constraint, which is actually basically if you take the DFT of over your ACF sequence, then all these guys, because they are actually power spectrum, they have to be non-negative. Okay, so our remaining problem is how we could actually guarantee that this thing happens. So our strategy is very simple. It turns out that what we do is that we do nothing. So why could we do nothing? Because even if we do nothing, in some condition, under some condition, we manage to prove that the probability that this non-negativity constraint is violated is quite small. So basically, it is high, there is a very high probability that this constraint is met. So why this happens? I will discuss that later. But before that, what we could summarize for this point is that we have this mapping that if you map from the ACF coordinate to the power spectral coordinate, you will see that this guy is actually a real valued bijection. So in that case, you still you don't really need a very weird input distribution in this coordinate. So basically, if this guy is a bijection, then the simple understanding is that the uniform distribution over the power spectral density domain is also translates to the uniform distribution in the ACF domain. So that will make our things quite simple, right? So that's the point. So now our finding is that if the non-negativity constraint is inactive, right? If it is met, then every side lobe coordinate can be modulated independently, and this guy will actually give us a very practical finite constellation modulation scheme. But before that, we have to prove that the probability that the non-negativity is violated is quite small. So before that, we first introduce how we actually modulate data onto the ACF domain, because that's not very intuitive, right? So what we do is that let us consider this thing on the frequency domain. So on the frequency domain, what we do is that, okay, we have this XP. So XP is the phase of the signal. The phase is simply drawn from a known PSK constellation, so we don't consider this part. On the right-hand side is corresponding to the amplitude or the magnitude of the spectrum, which is actually so conceptually, basically, it's the square root of the power, the so-called nominal power spectrum. So why this guy is called the nominal power spectrum? Because it is indeed the discrete Fourier transform, which is the DFT of the ACF sequence. However, this ACF sequence itself, as we have discussed before, it does not itself guarantee the non-negativity constraint, right? So that's why actually it's DFT. It does not guarantee, we cannot guarantee that this guy is a real vector and it's positive or non-negative. So in this case, the square root will give us some spurious results in some places, because in that places, this sequence can be negative, okay? So that's the point. But if we do, we ignore all these negativity, then we have this nominal ACF domain vector. It is actually because if you recall the property of an autocorrelation function, you will see that actually all autocorrelation functions are so-called conjugate symmetric, right? So that's why the first component we fix it into one, which is the main lobe, and after that we have this XS tilde. The XS tilde is something that is actually free. It's a degree of freedom because we could actually modulate anything on it. However, the other part, the part after it, has to be its conjugate symmetric part, right? So that's why we have to construct this guy according to XS tilde. It is not actually a degree of freedom. So this guy is fixed. It is basically the conjugated XS tilde and multiplied by this flip upside down operator, right? So All these symbols can be actually generated from any practical constellations. You could use anything that you like, okay? So this actually brings us a very different design philosophy from the original or the conventional communication society, because we simply put finite constellation symbols on the side lobes of ACFs, which is very weird, because in communication, what we do is that, okay, we could put random symbols on the time domain, we could put it in the code domain, we could put it onto the frequency domain, and things like that. You could put it on any domain that is a linear transformation with respect to your things like time domain, okay? All these domains are actually linear transformations from the time domain. However, what we consider here is actually a non-linear transformation, because ACF is actually a non-linear function of both the PSD, of both the spectrum and the time domain, okay? So now we turn to the problem. So how do we actually guarantee that the non-negativity constraint is met? So it turns out that there is a bound. We managed to prove this thing, that actually the probability that this non-negativity constraint is violated is exponentially small, as long as this guy is zeta of ACF, which is actually, if you recall, it is the attenuation factor of your side lobe is high enough, okay? So basically, if you make this guy quite small, in other words, if you're going to put all your ACF side lobes low enough, then the probability of this violation is quite small and is probably negligible, okay? That's our intuition. So in practice, what you could do is that I will give you an empirical value that if you set zeta ACF to 10, or in other words, 10 dB, then the probability of this violation is like 10 to the minus 4. It's quite small, okay? So that's the point. So after that, what we have managed to prove is that we managed to prove that in the high SNR regime, then the capacity can be expressed as this, because the ACFK, or the modulation scheme that we proposed, actually it does achieve this capacity, right? So we could simply analyze its achievable rate, and this is its high SNR achievable rate, which corresponds to the capacity. And this guy, if you look at it, you will see that on the left-hand side, this guy, there is a 2 over there's a 2n minus 1 over 2. So if you don't consider ACFK, if you consider a classical problem, then this guy is going to be n. So if you look at it, you will see that there is a degree of freedom loss, which is 1 over 2. So why does this happen? So it turns out that this thing is not very important, because this is actually the degree of freedom loss due to our hard power constraint. Because if you recall, we do fix our main lobe, but in the sense that it is entirely fixed, right? The energy of our code words are entirely fixed to a constant. But in the practical or other communication schemes, what we do is that we consider a expected power constraint. So that is not a hard power constraint. So by making this power constraint hard, we lose this 1/2 degree of freedom. But that's not the important part. The most important part is on the right-hand side. If you look at it, you will see that, okay, this part, this h bar magnitude square over sigma c squared, this guy is actually the original SNR. This is the original SNR that we could see from this channel. However, if you look at the denominator, there is a square root of this zeta ACF. So how could we view this? You could actually view this guy as a attenuation factor of your effective SNR. So you could see that, okay, this guy gives you a effective SNR loss, right? So so basically, if you're going to reduce PSL by a factor of zeta ACF, then your effective SNR is lost by its square root. So why is this happening? It turns out that we could actually understand this in a very intuitive manner, because you know that if you're going to increase the zeta ACF, then this guy actually denotes the reduction factor of the ACF. But if you consider Wiener-Kershin duality, then this guy also exhibits it as a elevation of the power spectrum, because if you're going to reduce your side lobe, then relatively your main lobe is somehow increased, right? If you consider this relativity, then from the power spectrum side, the increase of your main lobe corresponds to an elevation of the power spectrum. So what is actually the elevation of power spectrum? If you look at the right-hand side, this guy is actually the IQ plot of each subcarrier. So originally, if you look at an unelevated power spectrum, so if the power spectrum remains unelevated, then this IQ plot is going to be something like Gaussian. Why is Gaussian? Because on the ACF domain, we have randomly coded IID symbols. So the DFT that transforms the ACF to the power spectral domain, it is actually a linear combination. So by using the central limit theorem, what we have is that, okay, all these guys are approximately Gaussian. Okay, so it should be Gaussian in the first place, but if you are going to elevate, we are going to increase the power spectrum, what we have is that, okay, we move the mean from the origin to the outwards, right? So that's why this Gaussian thing becomes a Gaussian ring. However, the Gaussian ring has a width, right? It has a width. So it turns out that the width of this Gaussian ring is exactly controlled by this zeta, the square root of the zeta ACF. So that's why this guy, the square root of the zeta ACF, corresponds or is proportional to the logarithmic loss of your rate. Okay, you could understand this intuitively. Okay, so after that, we still need to consider the consequence of the non-negativity violation, because it is possible that it's violated, although the probability is quite small, right? So because the probability that non-negativity constraint is violated is small, we could actually have this assumption that there is at most one negative bin appears, because the probability that there are at least two negative bin is extremely small. Okay, so this event, the single violation, can be the dominant event. So what could we do with this? It turns out that we could actually use the same argument as we have used in the proof of the non-negativity violation bound. It turns out that we have managed to prove this thing. You see, if you look at it, you will see that, okay, we are actually trying to bound the so-called PSLR. So what is the PSLR? It is simply the ratio between the PSL and the main lobe level. So why is this case? Because if we have some non-negativity violation, then our main lobe level is no longer actually constant. So in order to consider the fairness, we have to consider the ratio between PSL and the main lobe level. And it turns out that we could actually bound this PSL very tight. And this guy, the probability that this thing is say is smaller than some value is exponentially close to 1. Okay, so that's why we could say that, okay, although the non-negativity violation can happen, we could conclude that the ACFK that we proposed has a high probability control on the PSLR. So let us consider something more tangible. So if you look at this numerical result, you will see that this is actually the empirical CDF of a PSLR. So the actual PSLR is in blue here, this line. So the ideal one is going to be a rectangular shape, right? It's going to be rectangular at this guy because this minus 42.9 is the design value of our ACF. So ideally, all the peak side will be at this point. However, because this non-negativity violation, we do not have this rectangular shape. It's slightly deviated. But if you look at the FC side, we'll see that, okay, this deviation is quite small, right? Because the largest possible deviation is less than 0.5 dB, right? So basically, the PSL degradation is rather small. So this is the sensing performance of our result. But if we go beyond a single channel use, we will see something different. Because basically, if you consider sensing, if you are familiar with sensing, then there is a technique called coherent processing or coherent integration over multiple channel uses. Or if you're familiar with communication, then the channel uses is something related to, say, OFDM symbol. So you could say, okay, if we would like to use, say, M OFDM symbols to perform a single snapshot sensing, then if we are going to reduce the ESL, then if you are going to average over all these channel uses, then it's quite simple that the ESL is indeed reduced by a factor of M, right? It's very simple. However, this guy does not really guarantee PSL control. So how do we actually control the PSL? So ideally, we could actually, we will hope that maybe the PSL is also reduced by a factor of M, right? So to this end, we actually extend the ACFK to the so-called AFK, which stands for the ambiguity function key. So this thing corresponds to the so-called fast slow time ambiguity function, which is a something very similar to the actual ambiguity function that is widely used in the radar literature. And this concept is proposed in one of our recent works. If you are familiar, if you are interested, you could read our work. Okay, so in short, we simply generalize our ACFK to this thing by simply considering the Wiener-Kirchhoff-like condition between the ambiguity function, this FSDAF, and the delay Doppler domain Fourier dual of the delay Doppler domain. So basically, what we do is that we simply design things on the ambiguity function. We simply modulate the random symbols on the side lobes of the ambiguity function, and what we do next is that we simply perform the so-called 2D FFT, right? We simply transform this guy to the time frequency domain by using the two-dimensional Fourier transform, or in other words, that is more familiar with to waveform guys. It's so-called the symplectic Fourier transform, right? Okay, so what we do know for this guy is that the nominal FSDAF will have this scaling of PSL. So in this case, we do have the factor of M, the PSL reduction. So that's what we hope to have, right? That's very good. So let us look at this numerical result. If you look at it, you will see that, okay, there is a 20 dB reduction of the PSL by upgrading this ACFK to AFK by using 100
OFDM symbols or 100 channel use. By contrast, if you don't use AFK, however, if you by contrast use the coherent integration of your ACFK, you will see that, okay, as shown here at by the dashed red line, you will see that the reduction is less than 20 dB, right? Basically the PSL is no longer confined because you use the coherent integration, which actually breaks your PSL control condition. Okay. So how do we actually implement this thing? It turns out that this is very simple, because on the transmitter side, this is something that we have actually introduced. So basically, what we do is that we split our data symbols into two streams, and on the top of it, we have this ACF branch. So this branch gives you XA, which is the amplitude or the magnitude of the spectrum. On the bottom side, we have this PSK, and we simply multiply them to combine them into one stream, and we take the inverse FFT and add CP. Okay, this is basically we have two streams of data. So on the sensing receiver side, everything is quite simple because this is the conventional structure. So this is basically a masked filter receiver for sensing. So we don't consider that so let's just skip that part. So for the communication receiver, things are a little bit different, because what we have to do is that we have to split this, the symbols into two streams, right? So for the first stream, what we do is that we just simply demodulate the phase symbols, the PSK. This is quite simple. However, on the bottom side, we have this so-called, if you look at it, we are taking the magnitude square of the signal, right? This is also known as non-coherent detection, because this guy will correspond to our ACF symbols. So this will actually complicate our analysis on the communication performance. However, what we could do is that we could consider a high SNR regime. So in that case, what we could do is that we could take the Taylor expansion. We could take the linearization of this non-coherent detection. So it turns out that we have this result, and this guy can be actually decomposed into three sources of errors. So this is basically the received ACF symbols, and we have three different sources of errors. However, the only dominant source is the second, because the first one is actually is negligible in the only dominant source is N1. It's only the first one, because the second one is actually negligible in the high SNR regime, because it's on the order of the square of NC, right? So it's quite small. And the third one is actually only non-zero when the non-negative constraint is violated, because the violation probability is quite small. This guy is also not dominant. So the only dominant source is the first one. So that's why we can actually compute the covariance of this N1 by this guy, and neglecting the correlations between these entries, which is quite conventional in the analysis of communication performance. We neglect the correlation between these entries, then we are able to obtain the effective SNR. If you look at it, you will see that, okay, this guy is actually the SNR as if this guy is a single carrier modulation. However, we are not considering a single carrier modulation. That's why we have this SNR loss. You will see that the SNR loss are related to something like zeta ACF and things like, basically this is the shape of your constellation, right? So let me give you a concrete example. You will see that, okay, if you have zeta ACF equal to 10 and your constellation is 32 QAM, then the SNR loss compared to single carrier modulation is around 15.3 dB. So you will say that, okay, this is very miserable. This is catastrophic. However, this is not, because we only actually need to accommodate only half of the rate with these ACF symbols. So that's why we can use a small enough order of the constellation compared to the effective single carrier modulation. So that will compensate for our SNR loss of 15.3 dB, right? So this is for the ACF branch. However, if you consider the PSK branch, then you will see that actually this is very, very interesting, that actually the ACF symbols themselves will give you an artificial channel fading. So these guys, these ACF symbols, will effectively can be viewed as a channel fading coefficient of these PSK symbols, and the distribution of this channel fading coefficient is the so-called folded normal distribution, because they are approximately normal, but because these guys has to be positive, right? So all these the negative part or the negative tail of this normal distribution is folded towards the positive part. So that's why it's called the folded normal distribution. So the observation is that you will see that if the SNR loss compared to the single carrier modulation in the ACF branch, then you will see that okay, the PSK is better, right? So we will see that there is a very interesting trade-off between these two branches. So if the ACF has a smaller effective SNR, then on the PSK branch you will have a weaker artificial fading. So you are going to have this trade-off. Okay. So finally, let's consider some numerical evidences of the performance of our results. So we consider this baseline. So the baseline is called the so-called generalized path, which is actually the so-called constellation shaping technique under the framework of ESL minimization. So in this case, the generalized path is something that actually controls the ESL of our signal. So our results are considering PSL. Okay, so it turns out that the communication performance of these two are relatively similar. If you look at the figures in the middle, you will see that okay, in both AWGN and Rician's channels, the OFDM PCS, which corresponds to the generalized path technique, if you look at the rightmost blue curve, this guy will have the similar achievable rate as our ACFK. You will see that okay, these curves are quite similar, and if you look at this guy, these curves are also so close. So you could actually conclude that the communication performance in terms of BER is similar. So that's actually our comparison benchmark. That's why we use this guy as a benchmark, because we have the same or at least similar communication performance. So that's why we can compare the sensing performance of these two. So if you look at the PSL, then everything becomes quite different, right? Because if you look at the PSLR of our ACFK, as we have proved, it is quite tight, because everything are just within less than 0.5 dB. However, if you consider OFDM PCS, which actually controls your ESL, then the PSL is quite wide, and its mean is on the right-hand side of it, and you will see that on average, you're going to have a large PSLR degradation, like 6.5 dB compared to our ACFK, right? So the last part is that how does this thing translate into target detection performance? Okay, so it turns out that if you look at this thing, this is quite vivid. So on the top part, you will see that the red curve is the threshold, and if you look at these two targets, there is a strong target and a weak target. So yeah, in the ACFK system, the weak target is clearly detected. But if you look at the generalized path system, then you will see that if you are going to detect this weak target, then you have a cost. The cost is that you have a lot of the false alarms, right? These are harmful. So that's why we have a better target detection performance in terms of the false alarm rate. So if you are more, if you care about a more statistical or more systematic performance metric, then you could look at this ROC curves. So if you look at this curve, these curves are actually the trade-off curves between the probability of false alarm and the probability of detection. So basically, if the curve is more like a rectangular shape, then it's better. So if you look at this, you will see that ACFK is always better than OFD and PCS, which controls your ESL, right? So this is the gap, and this is the gap, and this is the gap. So if we look at the gap, is quite prominent, is quite significant. So that's why we could conclude that the target detection performance of ACFK is indeed better because it controls PSL instead of ESL. Okay. So finally, I would like to recap on this talk. Basically, we have actually a conceptual separation from our existing works, in the sense that in most existing ISAC waveform design works, what we do is that we first choose the communication modulation scheme. For example, we choose an OFDM, an OTFS, and so on. And after that, what we do is that we analyze its average sensing side lobes like ESL, right? And then we tune something like the statistics like the force moments, also known as the kurtosis, or some simple probability distributions, things like that. So basically the order is that we choose the basic structure of the system, and then we do some fine tuning on its perimeter. This is the old philosophy. But in ACFK, what we do is that we do this from bottom to the top. So we start with choosing a desired sensing performance metric. We choose a desired ACF domain support, and we simply put data onto that support. And then what we do is that, okay, we analyze its communication performance and see whether the communication performance is met. Okay, so what we do is that we basically design the waveform from the matched filter output scenario statistics and go backwards and analyze its communication performance. So this is the new design philosophy I would like to share with you. So there are still some limitations and open technical questions regarding this issue. For example, the non-negativity constraint is still not actually controlled. We only prove that it is violated only by a small probability, but we still need to actually control it in some severe cases. So also the receiver that we have proposed is only a very simple one that is very low complexity to implement, but the optimality is definitely not guaranteed. So you could actually design a better receiver, and also you could consider some frequency selective channels, because in that channels we do not have our capacity achieving result, right? If you recall that the ACFK is only optimal if you consider the frequency flat channels. So you could also consider some coding and distribution matching and Doppler issues if you wish. And to summarize, we have actually formulated the waveform design problem as a mutual information maximization under PSL constraints. And we managed to prove that at SNR, high SNR, this problem is it becomes a uniform input distribution, and that gives you the capacity, asymptotically capacity achieving input distribution. So changing the coordinates from the PSD to ACF, this gives us ACFK. The ACFK actually implements this guy using finite ACF domain symbols and some independent PSK, and it's very simple. And the result is that this guy can give you a high probability PSL control, and the BR is competitive to the benchmark techniques that actually only control the ESL. Okay, That's all for my talk. Thank you all. If you have any questions, please feel free to ask.
Okay, thanks, Professor Xiong, for your wonderful talk. We do have received quite a number of interesting problems from questions. So let me first ask the first one. So given that P is an intersection of a simplex and the quadratic sidelobe constraints, what is the computational complexity of exact uniform sampling from P, and how does it scale with N and the number of active ACF constraints?
Yes, that's a very interesting and very good question, and it's very insightful. So we have kept looking at this problem, because we also aim at a precise sampling from this uniform distribution. But it turns out that the main difficulty is not the sampling, because if you're going to sample from this polytope, it's quite simple, because you could use so-called MCMC technique, right? You could use Monte Carlo Markov chain to speed up your sampling. The point is that if you're going to sample from this polytope, then what you get is actually a random codebook. So as I have mentioned, if you're going to use the random codebook, then the complexity of your decoding is exponentially high. It's not practical. So you cannot actually end up with some random sampling of that polytope. What you have to do is that you have to construct a structural codebook that admits a very low complexity encoding and decoding algorithm, such as ACFK. Because in ACFK, what we do is that we simply modulate IID symbols, and it's very simple. Okay, if you get the point. So of course, it's a very interesting question, because we're still looking at this problem. But at this point, I will have to say that I do not have a good answer to it.
Okay, thank you. Then, I myself also have a question regarding this slide. So here you mentioned the frequency flight channels, and also if you can see the frequency selective channels, then the optimal input distribution should be channel dependent. Let's see. So, indeed. So how shall we adjust the input distribution in that case? Can we just do something like a water failing over the let's see, this IID data distribution or uniform sampling over that intersection of simplex and quadratic sidelobe constraints?
That's also a good question, but I don't have a simple answer to it, because if you look at this distribution, you will see that this is not something that you could actually separate each entry from another. So that's why you cannot really use a water failing like regime scheme to achieve this thing, because so let me explain this thing, because this is actually the optimal distribution. This is not the objective function. So you have to achieve this thing by exactly you could say that distribution matching, right? You have to match your distribution to this thing. But as you can see, this is clearly not independent across these entries. So that's why you cannot use water failing.
Really? Okay.
You get the point. Yes.
Okay. Yeah. Okay. So another question from the audience: for even n, so you have n and even n. So can the in-circuit zero be replaced by an information-bearing symbol without violating sidelobe constraints?
Yeah, that's also a good question indeed. You're right about it. If you, sorry, let me try and find that slide. That will be okay. That will be this slide. Yes. So this entry can be actually you could simply replace that with any real number. You could use a real number there, because you have to keep this sequence conjugate symmetric. So in the even case, this point has to be real because it has to be kind of complex conjugate of itself, right? So if you look at the capacity result, you will see that this is also written there. Let me see where it is. If you look at the result, somewhere. Oh, sorry, I just cannot find that equation. But actually, you could basically you could use any real number there. Okay.
Okay. That's quite clear. So another question. So how does the transition from one-dimensional ACF to two-dimensional AFK fundamentally alter the trade-off between ESL and the PSL, given that coherent processing over M-channel uses reduces ESL but leaves PSL uncontrolled?
Okay, that's also a good question. So let me turn to that page. If you look at the, sorry, this is quite late one. If you look at that, okay, this one. So basically, the AFK is something what we're trying to do is that if I try to draw on this thing, let me try and draw on this thing. Okay, so the AFK is something that you do this modulation over a two-dimensional plane. Okay, so this guy is your delay. This is your delay. And this guy is your Doppler, and I will write it in short. So what we do is that we take its 2D FFT. We take the so-called simplicity Fourier transform, and this thing will become the so-called ambiguity function. The ambiguity function is on this domain. But if you take the 2D FFT, what you have is actually the time frequency domain. Sorry, actually the frequency slow time domain, right? So this Doppler becomes the slow time. The slow time corresponds to the sample period of your OFDM symbol. That's time scale. And on this scale, on this axis, what you have is the frequency, right? So this is something that you typically modulate on use OFDM, right? If you use OFDM, you're actually modulate something on this domain. So what we do is that we actually modulate things here. We modulate things here, and what we do is that we take this main lobe fixed. We take this main lobe fixed, but we take the side lobes actually controlled by the same way using the as we have applied in ACFK. And what we do is that we just use the 2D FFT to modulate everything else on the slow time frequency domain, because in this case we still have to use the PSK branch to multiply on this thing, right? We have to still have to do this thing. So consequently, what we managed to do so is that which is more related to your question, that everything we do here gives you a predictable AF, right? The AF is something that is predictable, like a plane here, and there is a thumbnail here. It's like a plane. But if you don't do that, if you do a coherent processing, what you have is something like this. It's actually fluctuating over the delay Doppler domain. If you get my point, right? So the fluctuation is very harmful, especially for our PSL. So what we do is that we simply control that fluctuation and confine them below this plane. Okay, so that's all for my part.
Okay, so there's a final question from the audience. Under identical ESL constraints, what fundamental property of ACFK enables PSLR concentration near the designed ceiling, while generalized PAS exhibits high and wide PSLR dispersion?
Sorry, Sorry, I didn't really get the point. Can you read that again, especially
so
the initial
under identical ESL constraints. So if we compare the ACFK with the path, okay, generalize path. So what's the fundamental property of ACFK enables PSL concentration?
Okay.
But the path explains wide dispersion of the PSLR.
Okay, I will explain that in a very intuitive way. Let me explain this a little bit. But I cannot give you a firm answer. I can only give you an intuition about it. So basically, if you look at this thing, okay, this thing is a IQ version of your PSD, right? This is the IQ version of your frequency domain. So it turns out that what we do is that we actually control everything. We control everything firmly in the ACF domain. If you look at the ACF domain, everything is controlled firmly because you're using very clear constellations, right? Everything is below that point. But if you transform this thing through an FFT to this power domain, power spectral domain, then what you have is that something is dispersed, right? You will see everything is dispersed. So basically there is a duality. So if you control ACF quite well, then everything becomes dispersed in the power spectral domain. However, if you do the opposite part, things will also be the case, right? Because if you're going to control explicitly in your frequency domain, then you will see that, okay, the ACF domain will be dispersed. There is going to be a dispersion. So it turns out that how could you actually implement generalized path? So generalized path is actually implemented using your original constellation, things like this. So itself is indeed very clear, it's very controllable in your frequency domain because it's just assigning different probabilities to these points, right? It's assigning different probabilities to these constellation points. But in its nature, it is still very discrete and it's controllable and not dispersive in its frequency domain. But if you go back to the ACF domain, then everything becomes dispersive. I hope I interpret this well. If you could appreciate it. Okay.
Okay. So a final question for myself. A little bit of future work on this current ACFK framework. So now we build all this ACFK signaling over the discrete, region. So what if we can see the continuous signaling? Can we also explicitly control the sidelobe, or in that case, what will be the achievable rate with a explicit PSL constraint?
I guess it's also a very interesting direction to follow. But I would say that we can take a little step back. We can just do something simpler, because what we could consider is that we could actually do the constellation shaping on the ACF domain. So in that case, maybe we can somehow ensure both the controllability on the frequency domain and the ACF domain. So that's only a imagination from my side.
Okay, that's quite interesting. Okay, I think that's all for today's talk. Let's thank Professor Xiong again for bringing us this very, very interesting new win from ACFK, and we wish that this framework can be extended more in the future, and we can have more advanced transceiver design over the current siting. Okay, so that's all for today's talk, and thank you again for listening. I think yeah, that's it.
Thank you, Professor Liu.
Okay, goodbye.
Goodbye.